First of all, let's establish the scenario found in pre-salt reservoir. As we all know, water injection is the most used method for secondary oil recovery. In our projects, dessulfated seawater is usually chosen to avoid problems with scaling and souring. Due to the presence of high amounts of CO2, WAG injection became a very good option. It's a way to deal with all the CO2 that's going to be produced and also to enhance oil recovery. Pre-salt reservoirs are formed basically of carbonate rocks that are reactive to injected fluids. The reactivity is increased by the presence of CO2 and can be affected by temperature and pressure. Reactivity causes changes in the composition and pH of produced water. It can also affect porosity and permeability, especially in the injection zone. Kinetic and thermodynamic parameters for the reactions are hard to obtain and are normally available in surface conditions. Experimental work was also developed to determine the parameters in reservoir conditions. Now, let's talk about reactive transport. The definition is pretty simple. It's the transport of a species in the porous media. But what does that mean? Well, let's take this simple example. When we don't have reactions in the reservoir, the produced water is going to be a mixture between injected water and formation water that is present originally in the reservoir. But when we have reactions taking place, which is the case for carbonates, this is no longer true, at least not for all the species. For some species, the produced water is going to be a combination of injected and formation water, but it's also going to have these reaction products. So this needs to be taken into account in order to have a good prediction for produced water composition. Just to summarize, in case of the carbonates that are reactive under fluid injection, water interacts with the reservoir rock, changing produced water composition. The inclusion of those chemical reactions is mandatory for carbonates. This kind of modeling is called reactive transport in porous media, and it's what we do every time we need to establish the composition of produced fluid when dealing with WAG injection in pre-salt conditions. To illustrate what I just said, let's take a look in the injection of the sulfated seawater in a carbonate reservoir. First of all, we have the dissolution of the CO2 in the water. The CO2 can come from the oil or from the reinjected gas in the case of WAG. So the CO2 is going to pass to the water and is going to cause a decrease on the pH due to the release of the H plus ions. If we stop right here, we're going to have a low pH in the produced water. But it's not what happens when we are dealing with carbonates. In this example, the reservoir is made of calcite and dolomite. So the H plus that is released by the passage of the CO2 for the water is going to attack the rock, causing its dissolution. Here, for calcite dissolution, the reaction number 1, we have the H plus attacking the calcium carbonate and releasing calcium and bicarbonate. So the amounts of those ions, calcium and bicarbonate, is going to be higher in the produced water, as well as the pH when compared to a scenario where we don't have any kind of reaction. The same thing is true for dolomite, but in this case we have this mixed carbonate of calcium and magnesium, so we have the release of calcium, magnesium, and bicarbonate, increasing the concentrations of those species in the produced water and also the pH. As mentioned before, experimental work was done to obtain the parameter for the reactions. On the left, we have a schematic of the reactor that we used. It was a reactor made in alloy to be able to deal with big amounts of CO2. So in this reactor, we can put rock, fluid, and also gas, and sample the water to obtain the growth and the changes in the composition through time. On the right, we have a representation of a test result. In this case, the rock was pure calcite. We work in a pressure of 4,000 psi and 60 degrees Celsius of temperature, and also in the presence of CO2. As we can see, only the pink dots show changes in the composition. The pink dots represent the concentrations of calcium through time. The growth means that calcite is being dissolved until a plateau where the reaction reaches equilibrium. All the other species that were analyzed, magnesium, sodium, and chloride, show no changes in concentration through time, meaning that they don't take part in any reaction. Only calcium is changing, and also bicarbonate that is not being shown in this graph. Besides laboratory experiments, we were able to run a field tests to show the effects of rock-fluid interactions. So we had a backflow test in a well. We injected a volume of water, closed the well for a while for a soaking period, and produced the water again. The graphs show the variation of concentration for calcium and bicarbonate in milligrams per liter through time. On the left, we have the result for calcium, on the right, the result for bicarbonates. The blue line represents a non-react case, which means that is the values we would expect for those ions if no reaction was happening in the reservoir. The red dots represent field data, which means that those values were measured during the test. We can see that's a huge difference between the field data and the no-react case, showing that calcite dissolution was real under reservoir conditions. To estimate the pH of a fluid in contact with rock in the presence of CO2, we use a geochemical software called ArcSym. To check if the values that were being estimated by the software were okay with the reality, we have a special reactor with a pH electrode inside. That means we can measure the pH inside the reactor in reservoir conditions. So the results of the tests are shown in this table. The first test was only water and CO2. It's a salinity of 30,000 ppm, that's compatible with the sulfated seawater, saturated in CO2. In this case, we don't have any rock, so we only have the CO2 in the water. The measured pH was 3.07 and the estimated pH 3.12. The second test was the same water, but instead of CO2 N2. The pH was much higher, 6.1 the measured pH and 6.17 the estimated pH. And the last one is the most interesting test, the same water saturated with CO2, but in the presence of calcite. In this case, we expect calcite dissolution to increase pH, which really happens. The measured value for pH was 4.53 and the estimated value for pH 4.51, showing that the predictions of the software are very good fit with the measured values. To see the changes in permeability, we have reactive flow tests. In those tests, we can inject a water with or without CO2, and we can analyze the composition in the outlet of the plug. This is an schematic of the plug flow test, and here is a picture of the equipment. On the left, we can see the variation in the composition for calcium, magnesium, and bicarbonate. In this particular case, we had mainly dissolution of calcite, shown by the values of calcium bicarbonate that are pretty high and the low amount of magnesium compatible with the sulfated seawater. On the right, we have the variation for mass and permeability. For the mass, we can estimate the variation by the changes in the composition. For permeability, we can estimate the permeability by measuring the pressure and the flow rates. We can see here at the end that we have a big growth in permeability, and at a point we weren't able to measure anymore. It means that we have a wormhole connecting the inlet and the outlet of the plug, so we can no longer measure the pressure, and permeability goes to infinity values around 60 pore volumes injected. Until now, we have been discussing the injection of the sulfated seawater, but now we're going to see what happens when we work with seawater. So, the main difference from seawater to the sulfated seawater is the sulfate amount. It goes from 2,800 in the seawater to less than 100 in the sulfated seawater. But we also have a big change in magnesium. It goes from 1,400 milligrams per liter in seawater to values that can go as low as 80 milligrams per liter in the sulfated seawater. So the difference in the amount of these two components cause two different reactions that we can see only in seawater and especially in high temperature reservoir. The first one is dolomitization, represented here by reaction number 2, is the conversion of calcite in dolomite. It consumes magnesium and releases calcium in the water. And the second one, represented here by reaction number 3, is anhydrite precipitation. It consumes calcium and sulfate and forms anhydrite in the reservoir. Reaction number 1 is calcite dissolution that happens also with the sulfated seawater and seawater. When we first started studying the injection of seawater, we had a doubt regarding dolomite. We saw in the reactor tests that magnesium was being consumed, but we didn't know exactly if the reaction taking place was dolomitization or just the precipitation of dolomite. And what is the difference? Dolomitization is represented on the left. It happens with consumption of magnesium and release of calcium, as we can see by the equation. On the other hand, dolomite precipitation happens as the equation on the right, and it consumes calcium as well. So when we are dealing with seawater, it's very important to guarantee that the sulfate that is being injected is going to be trapped in the reservoir on the form of anhydrite. And we can see by those mechanisms for dolomite that we can have a big difference depending on the mechanism that we take into account. If we look to the left for dolomitization, calcium is being released. It's as a communal effect, it's going to help anhydrite precipitation because we're going to have more calcium to be precipitated alongside with sulfate. If we look to the right on dolomite precipitation, calcium is always being consumed. So they are going to compete for the same calcium, both dolomite precipitation and anhydrite precipitation. And as we favor one, we are going to stop or make the other one weaker. So it was very important to find out which mechanism was going to take place under reservoir conditions. Dolomitization by releasing calcium and helping anhydrite precipitation, or dolomite precipitation that is going to consume calcium and makes the anhydrite precipitation harder. So we held a series of reactor tests, putting sulfate and magnesium and removing one of them, and we came to the conclusion that when we have magnesium in the water, the mass of anhydrite precipitation was 2.95 grams. When we didn't have magnesium but kept the same conditions, the exactly same conditions, we had a precipitated mass of 2.05 grams. As we can see, with magnesium in the water, we had higher precipitation of anhydrite. As we had exactly the same conditions, we can say that the mechanisms that was acting there, it was dolomitization. And that's why it was helping anhydrite precipitation, and that's why we have a higher mass of anhydrite when we have magnesium in the water. So the conclusion of those tests was the presence of magnesium increases precipitation. Therefore, we can take dolomitization into account and not the precipitation of dolomite. To validate the models for seawater injection, we have some field data for 2 wells in a reservoir where seawater has been injected. This is a high temperature reservoir, so the results are very good. Here we have the sulfate and magnesium in milligram per liter as a function of injected water in the produced water. We can see in both graphs that we have a dark red curve representing a non-reactive scenario. That means that in this case, the produced water is merely a function of the mixture between injected water and the formation water. For sulfate and magnesium, we can see a growth in the concentration due to the high values of sulfate and magnesium in the seawater. The blue circles represent the result of the reactive model. So for the reactive model, we have both reactions happening. The dolomitization that is consuming magnesium and the precipitation of anhydrite that is consuming anhydrite. The red triangles and the green square represent real data. So those are results that were measured on the field for two different wells. We can see that for both sulfate and magnesium, field data is much closer to the reactive model, showing that consumption of sulfate happened due to anhydrite precipitation, as well as consumption of magnesium due to dolomitization. These results can prove the modeling that we have been using for seawater injection. To represent the importance of rock-fluid interactions, we have here a little schematic to show where we work and what our results can help to predict. So we have both experimental and simulation works, and everything is connected. Everything that goes to the simulator, the parameters, and the reactions, all the understanding that we have and we put in the simulations comes from experimental results. And when we run a simulation, we can be looking for two main things: composition and pH of produced water, and change in porosity and permeability near well. For composition and pH of produced water, the results can be applied to material selection because the pH, we have talked about that and we have seen that the pH in the produced water is bigger when you have chemical reactions happening in the reservoir. So we can be using materials that are less expensive than we would have to if we didn't have any reaction going on. And mainly that produced water composition are for scaling prediction. So as we said before, those reactions change the composition of produced fluid and they have to be taken into account in order to have good scaling predictions. And also to evaluate if we can bypass the SRU, so if we can inject seawater alongside with dessulfated seawater, or if we can inject only seawater, and studies like that. And regarding the change in porosity and permeability, those studies can help a geomechanic. We can see if the changes caused by reactivity can cause changes regarding mechanical properties of the rock, and also for injectivity. That's a very important parameter because we always need to inject water in the reservoir, and some reactions can help the injectivity and can allow a higher injection of water in the reservoir. And we are also working a lot now with history matching in terms of composition. So we get the data from the field, the composition data from the field, and then we go back to the models to see if the results that we are generating in the models, if they are correct, and try to find out what's going on if they aren't. For example, if we're making a mistake in the assumption of mineralogy or something like that. And then we have to produce better models in order to have a good matching, and therefore, in the end, we have more reliable reactive transport simulations. Now we're going to see some simulation results for a WAG injection. On the left, we have a picture of the injector well for a case of 80% of CO2 in the injected gas. The property is diporo, that is the final porosity minus the initial porosity. We have porosity changes due to dissolution of calcite. So in the injection zone, the porosity is expected to increase, as we can see by the colors in the blocks that are signalized by the arrows on the left picture. On the right, we have a graph for block 13, that is the one that has shown the biggest variation in the porosity. On the graph, we see the variation of calcite fraction through time. We have four different scenarios: a non-reactive case for 80% of CO2 in the gas. In this case, there is no reaction taking place in the reservoir. That means that we don't have calcite dissolution, and therefore the calcite fraction is the same all the time. For the other three scenarios, we have calcite dissolution, but we have the effect of the amount of CO2 in the injected gas. The higher the value of CO2 in the gas, the more reactive the system gets. So the variation for calcite fraction is bigger for the case where we have the higher value of CO2, that is 80%. The smaller variation is observed for the case where we have 20% of CO2 in the injected gas. The 50% gets in the middle. So we can see that the light blue curve is higher in terms of calcite fraction than the green one that is higher than the red one, which means the red one is the most reactive case due to the amount of CO2 in the injected gas. On the previous slide, we saw the changes in porosity and calcite fraction for the WAG injection. Those changes are expected in the injection zone. Now we are going to analyze the changes in the produced fluid. On the left, we have the changes in calcium concentration through time. On the right, we have the pH changes through time. All the scenarios are the same as before. Non-reactive for 80% of CO2 on the gas, reactive for 80% of CO2, 50% of CO2, and 20% of CO2. As said before, the most reactive case is obtained for 80% of CO2 in the injected gas. Therefore, the concentration of calcium is expected to be higher in the produced water for this particular scenario, is what we can see by the red curve on the left graph. For the 50% of CO2, we have the green curve, and for 20% of CO2, the light blue curve that are a little smaller than the red one. The smallest values of calcium are obtained for the non-reactive scenario, where we only have the mixture between injected water and formation water. For pH, the smallest values are also obtained for the non-reactive scenario. We have the mixture of the fluids and also the passage of the CO2 to the water and no consumption of the H+. So we have very low values of pH that can reach 3. For the reactive scenarios, we have a difference when compared to the calcium concentrations. For the pH, the biggest values are observed for the case with 20% of CO2 in the injected water. It means that we have a competition between reactivity and the lowering of pH due to the CO2 passage. So we have higher pH for smaller amounts of CO2 and smaller pH for higher amounts of CO2. And that's why we have smaller values of pH in the red curve. To finalize the presentation, some conclusions about what has been said. In carbonates, the injection of water can cause chemical reactions that will affect the composition of produced fluid. Those reactions can be even stronger in the presence of CO2. Although the CO2 can lower the pH of the produced water, the reactions are going to increase the amount of bicarbonate and consume the H+, so we have much higher pH in a reactive scenario. Laboratory tests and field data confirm the extension of reaction under reservoir conditions. Dessulfated seawater and seawater can affect the system in different ways depending on temperature, pressure, and CO2 amount. As we saw, when we have seawater and high temperature, we can have two reactions that don't happen with desulfated seawater: dolomitization and anhydride precipitation. In order to have good predictions for produced water composition and pH, reactive transport models are mandatory. So every analysis that we need to do for carbonates have to take into account the reactivity of the reservoir and the changes that it's going to cause in the produced water composition.